Hello and welcome to the Daily Space for today, April 29th, 2019. I am your host, Dr. Pamela Gay, and I am here to potentially confuse you today. My goal is to put science in your brain, but we're going to take on a single story today, and I'm going to try and make sense of it. But this is a story. Thank you, Morgan. Thank you so much. I would totally throw bits to dogs, except all my dogs are asleep on the first floor of the house. Thank you for the bits. The audio is a little hollow sounding. Okay, I'm not entirely sure how to fix the audio sounding a little hollow. It may simply be a factor that it's Monday and everything is pretty much given up for the day. Alrighty, so last week a new story came out, or more, a new article came out building on data that we'd been seeing for a few years and first reported back in 2018 involving the expansion of our universe. The regular story that we've been listening to year after year after year is one of once upon a time, for reasons that are unknown, a single point expanded out to form the entirety of our universe. In that single point was contained all the mass, all the energy, everything that is or ever will be in this timeline. Now, what triggered that is a question beyond what many of us think science can answer at this point. We have no ability, given our current understanding, to observe anything from before our universe formed. And trying to understand what has occurred since that moment until now is the pursuit of many an astronomer. In that moment that everything expanded out, the entire universe was pure energy. And for the first few minutes of our universe, it expanded and cooled and expanded and cooled. And it went through a period of massive inflation, where the universe went from that pinprick in space and time to being the size of our solar system. And then it went through massive nucleosynthesis. This is Big Bang nucleosynthesis. And during this period of time, hydrogen, in this case, basically raw protons floating around by themselves, were able to collide and merge, and helium was formed and trace amounts of lithium and beryllium, and the universe expanded and cooled. And then, for a period of hundreds of thousands of years, the universe was too cold for nuclear reactions. It was too dense for, much to happen other than constant collisions. Photons were incapable of flying free. Electrons were incapable of binding to atomic nuclei. It was a soup of, energy, particles, and in the soup of energy and particles, there were sound waves ricocheting through the universe. And when this was all over, when it cooled and expanded enough that the electrons were able to bind to the protons, forming neutral atoms, in that moment, the light finally flew free across our universe. Thank you so much, Lady Pembroke, for the sub. Thank you. Now, that moment that the electrons and the protons were able to bind together to form neutral atoms, in that moment, all the light that had been released in the past collision, the collision that had just happened where it was reabsorbed and re-emitted, all that energy that had just been emitted a moment before, suddenly just kept going. It was no longer being reabsorbed every moment. And that light held fossilized in its colors the temperature of the universe where it had been at the moment that the cosmic microwave background was released. Now we combine all of that data. Thank you, Anonymous Chair, for the bits. Thank you. I have no dog to show you today, so I I hope my thanks is enough. Um, in that moment, as the cosmic microwave background flew out across our universe, thank you. Um, in that moment, the cosmic microwave background was released, and locked into the sky was an echo of all those acoustic waves, those sound waves that had permeated through that early first dense universe. So that's how we understand the first few hundred years of our universe. Now, in recent times, as we look out and about around us, we see stars, we see galaxies, and we get to watch, well, what has happened in the modern day and how that universe has evolved. And one of the tricky bits that we've been trying to figure out is how do we theoretically get from the formation of the universe to the universe we see today in a self-consistent manner that we can model in computers. And we are so close to being able to do it. But we have this problem that the story as we understand it, based on what we see in the most distant corners of the universe, based on what we see in that fossilized cosmic microwave background, that story doesn't precisely match what we see in our modern universe. And exactly why there's a mismatch? Well, for a long time, it could be, observational errors. But we can no longer blame it on that, as of last week. And this is what I'm going to try and explain to you today. So I'm going to walk you through the pieces. Now, here are the parts of the universe we're going to worry about. We're going to worry about the early universe, where it says, trying to find something on my screen that has the words big enough for me to read. So we have the Earth, we have the variable stars nearest us. There's an echo due to time delay. I wonder why I have an echo. This is all so deeply confusing. You should have no echo. Let me... Oh, I bet that I have Chrome going into something. Let's see if this helps. Let me know if this kills off the echo. And I will move my mic closer to my face. Alrighty. So, the part of the universe that we're worried about is this part right here. So we have, here's the Earth, and then we have the nearby pulsating variable stars called Cepheids. These stars are extremely bright, fairly metal-rich stars that exist places like the disk of our own Milky Way, the Large and Small Magellanic Clouds, and trying to accurately measure the distances to these stars so that we can use them to measure distances to more distant objects has been one of the great, how do we do this correctly, technical challenges of astronomy in the modern era. I have to admit, I actually remember going home my freshman year of university and telling my parents I was switching my college degree from international relations to astrophysics, and they were very concerned I'd never be able to earn a living. It turns out that was a realistic concern. But I remember explaining to my parents that one of the things I really wanted to do with my life was try and figure out how to measure distances accurately throughout our universe using variable stars. Now, in graduate school, I was encouraged to go explore the more distant universe and do things that were more easily funded. But this is the project that I remember as a young college student most wanting to see answered. And it turns out it's still something that we're working to answer today. But it looks like we've gotten as accurate as we can get. So here's what's going on. These massive stars, their outer atmosphere is expanding and contracting and expanding and contracting in a way that is driven by the absorption and re-emission of photons in their outer layers. So as these stars contract, the outer layers of the star begin to absorb the photons that are emitting from the center. And as they absorb these photons, it builds up an energy reserve. And later on, as the star starts to contract out, those reserve photons push the atmosphere out even more, driving this oscillation. There is a narrow band through our what we call color magnitude relationship, and any star entering this band of precisely balanced temperature and size, or it's mostly just temperature that matters here, have this feature in their atmosphere where they can reserve energy to drive oscillations. And the outer layers of the star actually act like a musical instrument, where the size of the atmosphere, just like the size of an instrument, dictates what kinds of frequencies, what kinds of pulsations are possible. Now, when we look at Cepheids, when we see a star that is pulsating very slowly for a Cepheid over tens and tens of days, this tells us it's an extremely large star, that it has a very large surface area, that it has a large luminosity. And this is something that has been measured in increasing detail over the decades since this was first determined by Henrietta Leavitt, working at Harvard College Observatory in the early years of the last century. Now, if you instead have a much smaller star with a smaller oscillating cavity, it's going to oscillate faster, just like you get that higher pitch from the soprano saxophone and the deeper pitch from the bari saxophone. Now, with these stars, if you look at this plot that I'm showing currently, which is from 2012, there's scatter. The stars are sometimes a little bit above the line, sometimes a little bit below the line. And that scatter in our observational understanding of this relationship means error in our measurements of distance, because we can, at huge distances, see how fast or how slow these stars are pulsating. And using that knowledge of how fast or slow they're pulsating, we can use the relationship to look at how bright they appear and go from how bright they appear to how much light they actually give off and calculate distance. This is a topic I could do an entire show on. But the catch is our ability to go from how bright they appear to how much light they actually give off and how far away they are. That how far away they are, the error in that is directly related to how much scatter is in this line that I'm showing. And so the scatter in this line meant that we had a scatter in our understanding of distances to nearby objects. And if we're trying to measure the expansion rate of the universe by measuring the distance to nearby objects, we need to know exactly where those objects are. And so this scatter in the Cepheid variables meant scatter in measurements to nearby galaxies that hosted supernovae. And supernovae we can see to even greater distances than we see these Cepheids. There's this one kind of supernova, a type 1a supernova. In this particular case, you have a small star called a white dwarf star. This is the core of a star like our sun, that someday our sun is going to run out of fuel in its center, and when it can no longer maintain nuclear reactions, it's going to stop producing new light. And our sun and all the other regular stars out there are balanced precisely between light pressure pushing out and gravity pushing in. And this balance keeps the stars inflated. If you remove the light pressure, the star collapses down until it's other forces that prevent the collapse. In the case of white dwarf stars, it's actually the electron pressure. The electrons getting so close that they're like, okay, I'm going to use the Pauli exclusion principle and a little bit of other physics, and I'm going to push apart the other electrons. And this electron degeneracy pressure is what's supporting a white dwarf star. And the electrons can only do this to a certain point. And if a white dwarf star gets a little bit too massive, it explodes. And it has a set amount of fuel at which it does this exploding. And the way it gets that extra mass is some of these white dwarf stars are cannibalistic. They exist in systems of multiple stars. They gravitationally pull matter off of their neighbor. And when they get past this too much mass point, they explode as type 1a supernovae. And we can see these at vast distances. So the key is, if we can correlate the Cepheid stars so that anytime we see a star pulsating with a set period, we know exactly how bright it appears, we know exactly how much light it's actually giving off. We can use that difference to calculate the distance. If we can find a Cepheid variable in the same galaxy that a supernova has exploded, we can get to the distance of that galaxy, and now we start correlating supernovae explosions. And we now have a number of galaxies that we've seen supernovae go off in, that we can see the Cepheid variables in. We just need to fix this graph so there's less scatter in it. And that scatter comes from a number of things. It comes from using different telescopes that each have their own slightly different, ways of functioning, night to night and, mountain to mountain. It comes from, mostly it comes from using different telescopes and differences in the night sky. So what you really want to do is replicate this plot using stars observed above the atmosphere and always with the exact same telescope. Ideally, you want to do this using the Hubble Space Telescope for every single star. And the way the Hubble was designed, there's no really practical way to do that because, more than one person wants to use Hubble. And the way Hubble was designed to be used is you slew the telescope over to the field you want. You then find a bright star nearby. You lock the electronics to looking at that bright star, and that prevents the telescope from swaying or anything else while you take a long observation. Pulsating variable stars like the Cepheids are pretty bright. They give off a lot of individual light. This means you don't need to focus on them for a really long period of time. And so folks at Hubble and a bunch of astronomers, led in part by Adam Rees, who received a Nobel Prize for discovering dark energy as part of one of the supernovae teams back in 1998, they've been working to figure out how do we change how we use Hubble to allow what are called drift scans. So they, rather than locking on with the guide star cameras, are instead just using the gyroscopes on board to essentially flit Hubble all over, take quick observations of Cepheid variables. And I'm annoyed they didn't plot their data in their paper. I spent the morning scanning through this paper. But they've taken the noise that's in this plot and they've made it about the width of that dashed line. And this new relationship allows them to measure the expansion of the nearby universe like never before. So here we see what they focused on. They looked at Cepheids within the Large Magellanic Cloud, a nearby small galaxy. They have used that to calibrate the distances to supernova in nearby galaxies. And this has been used to measure the expansion rate of the universe. Okay, so all's well and good. We can see how the universe is expanding. Now we can only see these supernovae out to a given distance. And here, if you could zoom in enough, the yellow line, this yellow line right here says 180,000 light years. Right here says 24 to 100 million light years is the distances they're measuring. And then eventually we make it all the way out to, Well, a billion light years. And that's not very far in our 13-ish billion-year-old universe. So when we want to measure distances in the most distant parts of our universe, the oldest parts of our universe, we have to go back and look at that cosmic microwave background. And here's where the science is going to get super tricky. And I'm really simplifying this. Other professional astronomers out there watching, feel free to giggle at my attempts to simplify this. I'm doing the best I can, folks. Okay, so when we look at the cosmic microwave background, you've probably seen it represented in these reds and blues, such as is shown in the far right part of this diagram. That red and blue is showing the very tiny, tiny temperature variations in the universe at the moment that the electrons and the atomic nuclei finally bound together and the light stopped being reabsorbed and re-emitted over and over again and instead flew free. We're still seeing that light that was released in that moment. And those temperature variations, by measuring their size over time, starts to give us a hint of, well, what was the physical size on the sky? And this gets kind of messy. This is a process called baryon acoustic oscillations that we're worried about here. And this is an animated GIF of one acoustic oscillation dissipating through the early universe. So what's happening is you have, come on, repeat. You have this sound wave, and as it spreads out, it's spreading, and then the universe cools. And at the moment the universe cools, there's no longer any pressure driving this wave out. There's suddenly a whole lot less collisions going on. You don't have both electrons and protons separately flying around. And with that drop in pressure, everyone's like, okay, I'm good right here. I'm going to stop. Now, it's not just a single oscillation that was present in the early universe. It was actually an entire myriad of oscillations. And there's a really good discussion of this at galaxies-cosmology-2015wikidot.com. And for those of you watching live, I am trying to figure out where I had hid my link so I can pass it on to you. It will end up in the show notes on YouTube. So we had all of these different acoustic waves interacting, bouncing off of each other. And what they end up producing is this background of various sized hot and cold spots. And by measuring the actual hot and cold spots and comparing it to our theories, and measuring the sizes that we see these hot and cold spots to be, and comparing it to the predicted actual sizes. So we measure the apparent angular size. We know how big they should have been. And by measuring the angular size as it appears to be versus the physical size it should have been, that allows us to calculate a distance. Now, this is completely different than measuring the Hubble constant. This is a different way of getting at it. And this is what you want in science, is you want multiple ways to get at the same information. And what we have as we work with the cosmic microwave background, as we work with all these different things, is a whole series of different methods to try and get at the expansion rate of the universe. And what we have is multiple techniques using the cosmic microwave background, using the early moments of the universe and the related physics to get at one expansion rate, 68 kilometers per second, give or take. And then we have another method, the Cepheids and the supernovae, and other related things to get at the current expansion rate. And they don't match. They don't match even with their error bars. And it's now to the point of being Well, according to the paper, thank you, Isaac, dude. Thank you for the bits. Um, According to the paper, and here I am scrolling up to the top, this is a discrepancy of 6.6 kilometers per second per megaparsec of universe. And there is a 99.999% chance that this discrepancy in the results is real, that there's an actual change taking place. And this wasn't fully expected. Now, a lot of how our universe behaves isn't fully expected. And right now, you might be seeing a whole lot of different predictions out there that talk about how new physics is required to explain our universe. And when you hear phrases like new physics is required to explain our universe, if you're me, it's like, wait, do you mean new physics, or do you mean we need to expand our current understanding? What we need to do is expand our current understanding. The stuff we know pretty well, but it's an incomplete picture. And to me, at least, there's something different between an incomplete understanding and a wrong understanding. And I don't think we have a wrong understanding. I think we have an incomplete understanding. And there's lots of people who are already starting to identify things that seem to be possibilities. If neutrinos behave differently than our current understanding, that could explain this. And neutrinos, just to step back through recent history. So neutrinos are something that have only been known about for 100-ish years as theoretically possible. Took even longer. It was only more recently that we began to be able to even detect neutrinos. When I was in graduate school, we still didn't know if neutrinos had mass or not. We now know they have mass. And then it was discovered, wait, neutrinos change identity. They're able to rearrange the ratio of mass and energy to go from one type of neutrino to another while changing how they travel. Neutrinos are one of these things that we don't fully understand. And the idea that there are perhaps additional flavors of neutrinos, perhaps they interact in ways we didn't know, well, that's consistent with us not knowing, well, what is the particle out there that makes up dark matter? What is so many different things, from dark matter to dark energy to the expansion rate of the universe? There's something missing. And there's other possible explanations, and it's all laid out beautifully in the paper that I'm now going to drop the link into the chat for, by Reese and Company, that has just come out. And this paper was written so that anyone with a reasonable college level physics, astronomy can begin to understand it. And then you're going to have to start digging through the references to fully understand it. But it's an understandable paper, and it's well written, and it's pleasing to read. So don't be afraid. Now, I know a lot of you are going to be doing did you think of, did they think of? I know I went into this paper I wonder if, because I'm a variable star astronomer. No. So these guys are amazing technicians. And at a certain point, astronomy is something that is a craft. It requires technical skill. It requires creativity. And on the technical side of how do you use Hubble to get the best and most amazing results possible, these guys are the best there is. And this paper lays out the options for what it can be. Thank you for the follow, Exoskeleton. This paper goes through and does a beautiful job laying out, here's what you might be thinking. Here's our thoughts on this. Here's where the further study needs to be. Here's what past authors have said on this. Multiple Nobel Prize winners went into thinking this through. This paper has gone through peer review, and everyone who's read it has been like, yeah, this looks right. There's something wrong with how we have been thinking, and we need to expand our understanding. And this is why we do science. It's not because we know everything. It's not because we think we know everything. That would be awful boring to be a scientist if you thought you already knew everything. No, we do science because we want to know everything, and we have questions that we don't know how to answer yet. But we're going to give it our all, and in this case, we're going to find new ways to use the Hubble Space Telescope, or at least Adam Rees is, in order to figure out the universe a little bit better. So I kind of think that just like we all remember those papers that came out in 1998 detailing that there's this thing called dark energy out there that's going to make all of our math a whole lot harder. I think we're going to remember where we were in 2019 when it was realized that we can't ignore that we get two different values for the expansion of the universe, depending on which parts of the universe we look at. So, it's an interesting day. Our universe just got that much more curious. Curiouser and curiouser. This is why we do science. And that's all I've got today. One long story about one amazing paper and all the hundreds of people and papers and years of research that it took to get here. So thank you, and I am going to take your questions in just a moment. Before I take your questions, I'm going to remind you, if you ever miss an episode, we've got a YouTube channel. Check it out and give it a follow, youtube.com/c/CosmoQuest. Your subs on YouTube are completely free to you, and they really help us in the search engine algorithms. Please consider giving us a sub over on YouTube, again, completely free. And make it so that when someone's trying to understand the universe, they get the real science instead of all the weird stuff that tends to get watched a little too often and rise a little too high in the search engine algorithms. And please consider, if you can, helping to support our show. We love your bits. They mean the world to us. The best way you can financially support us is through a subscription here on Twitch or through a subscription over on patreon.com/CosmoQuestX. Now, while money does help me pay people, which really, that makes me sleep better at night, that's not the only way you can help us. Like I said, follow us over on YouTube. And in general, help get the word out. Tell your friends, inflict us on your neighbors. Share the word that there is this little channel over on Twitch and this channel over on YouTube that are here to put science in your heads. Spreading the word's really the single most important thing you can do to help us keep going into the far distant future. So thank you so much. We are, as always, a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We claim the rest of it as well. So thank you so much for watching. Thank you for the bits. I actually have a puppy that just came up. Come here. Come here. Ooh. And I don't have any Cheerios nearby, but I can show you the puppy. Thank you so much. Thank you so much. I have a puppy licking my nose. Okay, I'm not a Cheerio, but apparently I'm tasty. Thank you, Stella. Thank you so much for the bits. So I will now look for your questions. This is little Stella Sky. I don't know where in the house Eddie is, but I think he's still recovering. Oh, my Patreon slide is wrong. Okay, I will have to go fix it. So I don't know where Eddie is, but he's still full of Cheerios from Saturday, I think. All right, I am going to, while holding my dog, look for your questions to answer. Thank you for the sub, Lady Pembroke. Thank you, Anonymous Cheerer. Thank you, Morgan Johnson. I'm going to thank people again as I scroll through. Thank you, Kevlar 1066. Please don't lick me. You're going to lick me. Ugh. Why? Why do you do this? I love my puppy. She loves the inside of my ear. I'm sorry that I ate your pleasant reverb, Larry. So Larry Weird and Proud says, does your training in international relations help in your work? I think it does. It gives me more of a global perspective. It helps me understand the original, well, anytime you understand people's cultures a little bit better, it helps out, I think. It also means I understand economics more than I would like. It was economics and learning that it is more beneficial for a company to kill someone than maim someone that really was like, I don't want to learn any more about this. The universe, when it kills you, it's less cost benefit analysis about it. Okay, Astro YYZ asks, why do they use Cepheids in the LMC as opposed to in our own galaxy? So with the Large Magellanic Cloud, they are essentially closely packed together in the sky and all at the exact same distance, more or less. It's sort of like from here in St. Louis saying that everyone in New York City is at the same distance. While there might be slight variations, and those are what create the error bars in the new graph that they didn't put in their paper. With the LMC, all of the variables were all at essentially the same distance, and so they had one thing that they didn't have to worry about changing. Working in our own Milky Way galaxy, things are at all different distances. And so now you have to figure out how do you measure that. And so now you're talking about using parallax measurements for everything, and it just gets messier, and you're compounding, you're making it a more complex system. And my puppy is being adorable. So Larry Weird and Proud says, it is the change in the Hubble constant thought to be linear over time. We don't know. There is some evidence that the change in the Hubble constant over time is, well, first of all, we do know it's accelerating. We get to that from having dark energy, but it is thought that that acceleration also has a change in value over time. So the rate at which the universe is changing its expansion rate is also changing. Oh, lambda cold dark matter. I'm sorry. So a lambda CDM model means that you're doing a model of our universe that includes dark energy, and it assumes that dark matter is at the end of that first 400,000-ish years of Big Bang and the formation of the cosmic microwave background. At that moment, the dark matter isn't that hot, so it's not flying around with huge velocities. The cold is a reflection of what is the velocity of the dark matter. Let's see what else is in it. Do not lick my chin. You're gonna lick my ear more. Thank you for the bits, Blumbottle. I have no idea how to say your name. Thank you for the bits, Trucker Kev. Thank you, Refsmat. I love seeing all the emotes everywhere. Gildastar oh, you're pointing out that my Patreon URL slide is wrong. Yes, I will fix that. I am so sorry. I hope somebody typed the correct URL in. Yes, this pup totally loves her pack leader. So Ed Thompson asks, who do you think had the greatest influence on your loves of science? Oh, I'm sorry, I'm not projecting my voice loudly enough today. Okay, stop. Oh man, I don't know. Science fiction, oddly. I always wanted to figure out how did they do that thing in the movie? How could that thing in the movie have been possible? Yeah. Reading the story of the Harvard College women that was described by Timothy Ferris of coming of age in the Milky Way really had a lasting impact on me. Those stories shaped my desire to study variable stars, shaped my desire to work on the Hubble Key Project. Not that I ever did, I went in other directions. So I really think that the stories of those women were really what shaped me. Yeah, my. Can you hear me now? I'm sorry. Is my mic better now? Yes, Stella licked it. I'm so sorry. Okay, so you could hear me the whole time. That's good. That's so confusing. There's something definitely weird going on tonight. So Mike Cassidy, we don't know how dark energy and inflation are related. We just don't know. I didn't mean to explode, Larry. I have the happiest puppy ever. Okay, so do we have any more questions? And while you type in any remaining questions you have, I'm going to look and see who is streaming to think ahead to who I just might want to raid. Stop licking me. Oh, dog, I love you too. Okay, so I'm going to the Knowledge Fellowship to look and see who all is streaming. This is a Discord filled with people who are trying to educate through Twitch. So we have Demon Machine, me and Stella, Demon Machine again. Adam is streaming. There's someone called Midnight Duck. I wonder if they're still live. Bob Ross is painting from heaven. That is true. That is very, very true. So let's see. We have... Is Midnight Duck still streaming? Midnight Duck is no longer still streaming. So I think that we're going to raid Adam, who's doing programming. Our world is filled with Cheerio dust, Hanny's Warverp. So Astro B asks, is there any scientific reason why the universe could not be at least 2 times as old as we think and hundreds of times bigger? Well, so bigger, we don't actually know how big the universe is. We only know how big the part of it that we can see is. So the part of it that we can see, I don't think is going to be that much bigger than we suspect. Now, when it comes to the age of the universe, one of the confusing side results of the paper that just came out is it makes the universe potentially significantly younger, only 12 billion years instead of the currently thought 13 billion years. This is still consistent with stellar evolution. We have not made the globular clusters older than the universe again. We're good. But the universe's age could be different than what we think. Probably not a factor of 2, definitely not a factor of 100. That would break stellar evolution. But it's its own thing. Do you want down? Okay. There. And now the puppy is done. So, yeah, knowing how old the universe is and knowing how old stars are, these are all incredibly difficult problems. Okay, so I'm not seeing any more questions. I am set up to potentially raid Adam. I am looking now to run the credits. And I just want to thank you all again. Oh, here's String Terry asking, is the potential difference known to a good degree? Yes, we know that there is a little over 6% difference between the two expansion rates, and this leads to a potentially billion-year difference in age between roughly 12 billion years old and somewhere north of 13 billion years old. So it's all outlined in the paper. I'm going to link it in one more time. This is as readable a cosmology paper as I've ever seen. It's still not pleasant. It's still not easy, but it's the most readable cosmology paper I've seen, I think. One second, I'm finding the end credits. So Get a Star says, how big of an object would it take to produce a noticeable change in orbits of our solar system if it passed through without hitting anything? It would all depend on where it passed through. You can pass a black hole through our system just right, and it would require telescopes to see changes in orbits if it was a small enough black hole. We're going to detect it. It's just a matter of how quickly. Anyways, so Ed Thompson is like, what kinds of cores do we think gas giants like Jupiter or Saturn have, liquid or solid? Probably solid. They probably have a crystalline core of some sort. Okay, so now we're getting into all the questions, but really I'm going to go now. I love you all. I am fighting a pressure headache today, and cosmology and meteorology shouldn't be mixed within one brain pan. So I will see you all tomorrow when we return at 1 p.m. Eastern, 10 a.m. Pacific, 6 p.m. London time. And next week, just as a heads up, things are potentially going to be a little bit weird. I will be coming to you from Budapest, and Annie will be helping out here in the United States. So stay tuned for a little bit of chaos. But hey, it's going to be science all the way down. So wherever you are in the world, have a fabulous morning, evening, or afternoon, and I'll see you on the other side.